Okay, today I'd like to do another clearing type problem, but we'll be using some of the results that we've derived in previous videos, and I'll mention where we need those as they come up. So here's the goal. We have a cylinder or a sphere, or really any object that has a circular cross-section. Let's say the radius of this object is r, and the question is, if we launch a projectile from the North Pole, so this object is fixed at the origin, it's glued down there or something, and we're going to launch our projectile from the North Pole of this object under the influence of gravity straight down. And the question is, what is the minimum angle? So the angle we're talking about here is this angle, theta, the launch angle, relative to the horizontal, and minimum speed, v naught, so that this projectile just barely clears the cylinder, doesn't re-intersect it at any point. Minimum angle and minimum speed. Okay, now while we could try to do this with calculus, and actually I'll be honest, I did try to do this with calculus, and it was very, very, very messy, and I never really got a satisfying, clear final result. I'd rather do this with geometry. In particular, I'm going to use a couple facts about these minimal speed trajectories that we've derived previously. One of them said that if I take the distance between my launch point and my final point, and my final point in this case really means this point of tangency B. So my launch point is point A, and my tangent point is point B. That's the point I'm just barely trying to clear. The distance between those two is actually equal to the amount of deflection that the object has from its rectilinear motion. Now notice I could have drawn that here, something like right here up to wherever this intersects, but that's actually going to be the same as this distance here. There's a parallelogram, actually a rhombus, that you can quickly derive here. So I'm just going to backtrace this point B tangent along point V to where it intersects the y-axis. I'll call that point E. What we showed earlier is that if you're in a minimal speed situation, the direct line of sight distance is equal to the amount of deflection downwards. So we have an isosceles triangle. And actually, we can do one better. The velocity vector is orthogonal to and bisecting of the opposite side of this, the base of this isosceles triangle, in the case of this being minimal speed. So point D, where my initial velocity vector intersects this tangent line, is at a right angle. Those tangents are perpendicular. So knowing these geometric facts, we can start doing a little bit of angle chasing. And I'll go through some of the details just because it might have been a while since old geometry. Let's give some names to some of these angles so we don't have to keep on rewriting them. I'll call this angle alpha, say, right here. That's the angle between the horizontal and the radius drawn to the point of tangency of this parabola. Notice that that means that this will also be alpha because those horizontals, CB and the radius there, are both horizontal, they're parallel. Let's also call this angle up here maybe delta. And because this is an isosceles triangle, we know that this angle is also delta. Let's also give this the angle name gamma and this the angle name beta. So I've got all my Greek letters all together. So what do we know from this? Well, first of all, since OB is a radius and it's drawn to a point of tangency, we know that alpha plus gamma plus delta is 90. So this is a right angle right there. We also know from this right triangle that gamma plus beta is 90. We also know that since beta is an exterior angle of this triangle, what is it, EAB, that beta is actually going to be the sum of the remote interior angles. So beta is 2 delta. There's a beta is delta plus delta. Those two angles are the remote interior angles, and this exterior angle beta will be their sum. And finally, we haven't yet used the fact that this is on a circle. Since radius OA and radius OB are both radii, then we know that this angle beta and this angle alpha plus gamma have to be the same. They're both base angles of another isosceles triangle. So our last condition is that beta equals alpha plus gamma. Now I have 4 equations with 4 unknowns. They're all independent from each other: alpha, beta, gamma, and delta. And if we go through this and solve for what these angles are, we end up finding alpha, gamma, and delta are all 30-degree angles. In other words, these 3 angles trisect this right angle, 30, 30, 30. That also tells me that beta is 60. So you can go double check all that. I won't go through the algebra there. If that's the case, though, then this is 60, alpha plus gamma is 60, and angle OAB is 60. So we have a equilateral triangle here, 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 here. This is actually an equilateral triangle that is built into this circle. Knowing that angle beta is 60, that means this little angle that is complementary to it below the horizontal will be 30. And we also know that this total angle has to add up to 180. We can go figure out what the last angle in triangle EAD is, and it will turn out that since this delta is 30, this is 60. So I have 60 here, I have 60 here. We've got 30 here. That means that theta must be 30 degrees. So that's our first result. There's the angle that will guarantee this minimal condition of speed in a way that does not intersect the cylinder again. Then to find V naught, let's recall we had a formula earlier that said, we'd written it like this: V naught squared is G times R plus H, where R is the distance between 2 points, the launch point and the final point, in this case point B, the point of tangency. And H, in the original question we did, was the height of the wall we're trying to clear. Notice that in this case, our wall is down. It's not actually a height we're trying to clear above. It's a height we're trying to clear below. The result that we derived earlier still works entirely well. We just have to be very careful to remember that it's now a negative sign. So in our case, this R, little r, from A to B is the direct line of sight distance between the 2 points I'm comparing. And because that yellow triangle is equilateral, it's actually just equal to the radius of the circle. H, on the other hand, excuse me, is this distance from, let's say, AC, and it's negative because it's below the starting point. So all I have to do is find out what that AC is. Well, that's not too hard, since this triangle is equilateral, and we know that a perpendicular of an equilateral will bisect the opposite side. That must mean that AC is just half of the radius. So if AC is r over 2, and I subtract that, I'm going to get gr over 2 as my minimal launch speed. And there we have it. Fire it at a 30-degree angle and fire it with a speed of root gr over 2. And you will just barely clear this edge when trying to minimize that launch angle and launch speed. QED.